Hello guys. So today we are going to be covering a really important topic in electronics, which is transistors. Specifically, we'll look at the different types of transistors and then do a deep dive later on MOSFETs. So first thing first, what even is a transistor? A transistor is basically a semiconductor device used to amplify or switch electronic signals. Now there are several types of transistors, and this diagram gives us a nice overview of that. At the top level, we have transistors, which brown into three main categories: thyristors, triac, and the FETs. Now the FET or the field effect transistor further divides into MOSFET and JFET, and then we have the BJT, bipolar junction transistor, which comes in two flavors, PNP and NPN. There's also this IGBT, which kind of sits at the intersection of both the BJT and the FET technology. Today, we are going to focus mainly on the MOSFET, since it is the most widely used transistor in modern display circuits. So, MOSFET stands for metal oxide semiconductor field effect transistors. And as you can see from the diagram here, it's a four-terminal device. Those four terminals are the gate, the source, the drain, and the bulk. The bulk is also called the body of the substrate. The gate is insulated from the channel by a thin layer of silicon dioxide, as you can see here. That's the oxide in the name. This insulation is actually what makes the MOSFET so power efficient because almost no current flows through the gate. On the right here, you can see the different circuit symbols for the MOSFET. There are a few variations depending on the type. And down here, we can see there are a few variations of the MOSFETs depending on the type and how the bulk is connected, but they all eventually represent the same device. Now, let's look at how an N-channel MOSFET actually works, specifically in its on and off states. So in the off state, uh, the gate voltage is zero. The PN junction between the drain, source, and the P-type body are reverse biased, and so no current can flow. The transistor is essentially an open switch. While in the on state, we apply a positive gate voltage. This attracts electrons to the surface of the P-type body just beneath the oxide layer, forming what is called the N-type inversion layer or channel. This channel connects source and drain, allowing the current to flow. The transistor is eventually a closed switch. So in simple terms, gate voltage controls whether current flows or not. That's the fundamental switching action of a MOSFET. Now let us zoom into NMOS structure specifically. NMOS stands for N-type metal oxide semiconductor. As you can see in the diagram, the NMOS sits on a P-type substrate right here. The source and the drain regions are heavily doped N-positive regions embedded in this P-type body. The gate sits on top, separated by the silicon dioxide right here. A few key design parameters here are the channel length and the channel width. In most of the digital designs, actually, the L is fixed at the minimum feature size of the technology, while W or the width is something that the designer can tune to control the transistor strength. Also note that the bulk is connected to the ground in NMOS to prevent any forward bias PN junctions. On the right, you can see the simplified switch symbol, a closed switch for the on state and a open switch for the off state. Now, let's talk about the electrical characteristic of an MOSFET. The graph on the left, the graph on the top here, plots drain current versus drain source voltage VDS for different values of gate voltage. You can see as the VGS increases, as we are moving upwards, as the VGS increases, more current flows, and higher gate voltage means a stronger channel. The graph on the lower side here is called the transfer characteristic. It is a graph between IDS, the drain source current, versus VGS. Notice that the transistor does not start conducting until VGS reaches a certain value. That value is called the threshold voltage. Below VT, the transistor is off, and above it, it turns on. This is critical parameter in the MOSFET design. Now, the PMOS is essentially the complement of NMOS. Here, the substrate is N-type, and the source and the drain are P positive regions. PMOS has a negative threshold voltage, typically around negative 0.3 to negative 1.2 volts. And importantly, a PMOS transistor turns on when VGS is less than VTP, meaning it needs a low voltage at the gate to conduct. So it behaves the opposite way of the NMOS. The characteristics of PMOS are pretty similar in shape to NMOS, but they are mirrored about by axis. The terminal characteristics show IDS against VDS for different value of VGS here, and all voltages here are negative, reference with respect to the source voltage, which is assumed to be at ground. Finally, let us wrap this. Okay, so finally, let's wrap up with a really useful concept, the switch model of MOSFETs, which is how we think about the MOSFETs in distinct logic. Looking at this table, when the input is at logic 1, NMOS turns on and the PMOS turns off. But when the input is at logic 0, the NMOS turns off and the PMOS turns on. They're complementary. They'll always do the opposite. This is exactly why CMOS logic, which uses both the NMOS and the PMOS together, is so powerful and efficient. When one is on, the other is off, which minimizes power consumption. And that's the wrap. So to summarize, we covered the types of transistor, understood the structure and operation of both NMOS and PMOS, looked at their electrical characteristics, and finished with a switch model that's fundamental to digital design. Thank you.